and welcome to session number 72 of the Porous Media Design Talks. I am Chiara, and I'm joined. Hello, everyone, and welcome to session number 72 of the Porous Media Design Talks. I'm Chiara, and I'm joined here today in the studio by my friend Sang. We are part of the Interpol Young Academy and organizing members of the Porous Media Design Talks. And with this platform, we aim at giving the opportunity to early career researchers to present their work to the worldwide community of porous media. Today, we will have two great speakers. Our first speaker is Leonardo Sandoval. Leonardo is currently a postdoc at the University of Arizona in Tucson, where he's working with Professor Laura Condon. After his master's degree at the National University of Columbia, Leonardo moved to Politecnico di Milano in Italy, where he obtained his PhD under the supervision of Professors Monica Riva and Alberto Guadagnini. His research is focused on the use of numerical methods and optimization algorithms to support physics-informed decision-making while addressing the inherent uncertainty of natural systems. Leonardo's talk today will focus on large-scale hydrogeological modeling of the Po River district. So Leonardo, with this, the floor is all yours.
Thank you very much, Chiara. This is the title of my presentation, an integrated surface groundwater model of the Po River district. This study was done or conducted with the ultimate objective of advancing large-scale hydrological simulations for water management. Most of this work was conducted in the Politecnico di Milano in Italy, where I worked before, and in a strong collaboration with the University of Arizona, where I work right now. And the main motivation of this work is to answer the question how to best manage water resources in Lombardy. For those of you who don't know where Lombardy is actually the orange area that I have in the figure of the Italy map. And this question was raised by the Water Alliance group, which is a group of water managers in this region, which want to predict better what is going to happen with water resources in this area to plan actions that efficiently mitigate any climate change impacts on the region. Also, the Water Alliance is centralized in Lombardy region. We have the usual problem that administrative boundaries do not coincide very well with hydrological boundaries. So we decided that the best way to answer the question to Water Alliance or of how to best manage water resources in Lombardy was to build a numerical model of the water resources in this region. But we consider, or we decided to increase the domain of our numerical model to the entire Po River district. The Po River district encloses the natural watershed of the Po River, which is the longest river in Italy and one of the most important rivers in Europe. It has an area of more than 80,000 square kilometers. And in the valley of the Po River district, thousands of wells drill water or pump water for multiple applications, agriculture, industry, and domestic use, for example. Many of these wells drill water for depths that are greater than 200 meters. And the region is very important from the for the Italian economy point of view, because 40% of the Italian GDP is produced in this region, and 24 million people live in there. So what I want to show today in today's presentation is actually the story of how we built and calibrated this model. I want to highlight what I consider are very important points to successfully build this type of models, and just to present some outcomes of this work. So the first thing that I consider, or I think is important when you want to build a numerical model, is to actually ask yourself, why are you building this model? What is the purpose of it? Who is going to use it? Because I think that when you ask yourself these questions, you will actually decide what are the best tools for your model, what are the correct data sets that you should use in your model, and also what are the correct assumptions that you should introduce in your model. In our case, we were interested in water management. That means that we were interested in subsurface flow, surface flow, the interaction between these two water systems. Also, we are interested in understanding how the atmospheric forcings will play a role or will affect water resources in the system, as well as the soil use. What happens if the soil use changes in the system? And finally, we are also interested in pumping and irrigation. What happens with the anthropic interactions with the system? How are we affecting the water dynamics in the domain? So to answer all these questions, we decided to go, to represent all these processes, we decided to go with a numerical model called Parflow CLM, which is capable to represent all these processes. For the sake of time, I cannot go in all the details of Parflow CLM, all the equations that it has, all the data sets that are necessary to build a model. But I will focus on some points that I consider are particularly interesting for this model, or for this Por River district model. Okay, so I will start with the subsurface flow, which Parflow represents with the Richards equation, which are close with the Bange-Nuchten model equations. As you may know, when you want to perform a numerical simulation, you need parameters to predict parameters that tells you how your system is going to behave. Okay, and one of the first problems that we had when we were building this model is that we didn't know the values of these parameters. So we had to come up with a methodology to actually reconstruct the three-dimensional field of all these parameters that you see on the slide to actually conduct the simulations. We decided to do so using a weighted generalized mean to calculate effective parameters for each cell of our numerical model. How it works is that we will take in each cell of the domain the percentage of each geomaterial present in that cell, and we will multiply that percentage by the actual value of the parameter associated with that geomaterial. Okay. This allows us to obtain an effective parameter. And when I say an effective parameter, I refer to, for example, an effective hydraulic conductivity, an effective porosity, and an effective Bange-Nuchten parameters for the entire system. So this is the methodology that we follow, but as you may imagine, obtaining the fractional composition of different or diverse geomaterials in each cell of the domain is itself a very hard task. But we were lucky because we were a big team, and we could rely on the results of previous research. Specifically, I could rely on the geological reconstruction that was conducted by my colleague Andrea Manzoni of the geomaterials in the Po River district. Using this information, we were able to recover the fractional contribution of 6 different geomaterials. These are gravel, sand, silt, clay, permeable and impermeable rock in each cell and each layer of the domain. We constructed a model of 6 layers, and the information that you can see here is summarized also in this figure here, where you see that for each layer of our domain, we have the fractional composition of each one of these geomaterials. Okay. Here is in this scheme, I try to represent, this is a scheme that is not in scale, but I try to represent the actual composition of the geomaterials in the complete domain. Because our numerical model has 6 different layers, and each one of these layers has a different thickness. The first layer is the thinnest layer. The first layer is the uppermost layer of the domain, so closer to the surface. And the second layer is thicker than the first one, and the third layer is thicker than the second one, and so on and so forth. We did so because we expect that the highest gradients of hydraulic head in our domain are located in the uppermost part of the system. So we want to represent better what is happening in that area, and we try to increase the resolution over there. So that's what we did to recover the hydraulic, all the hydraulic parameters of the source of subsurface. A similar procedure was followed for the surface flow, or for the atmospheric forcings, for the soil use, and also for the pumping and irrigation that I found particularly interesting. So I will explain a little bit more about them. So for the pumping and irrigation, we collected information from multiple sources, official and non-official sources. And when I say non-official, it means non-government non-government institutions. And we were able to estimate maps, so spatially distribution maps of water use in the system, especially groundwater pumping. We were very happy because the values that we estimated, we were very close to the official figures that you can see in parentheses for domestic use and agricultural use in this slide. But with the big advantage that our estimates have this spatial distribution. So are closer to, or are in theory, are closer to reality. A similar procedure was followed for the irrigation that was estimated from datasets of Dari et al. In 2023. In this case, we estimated a total of 16,000 millions of cubic meters per year, and the official figure reported by authorities in the area are 16,500 millions of cubic meters per year. So again, we are very close to the official figure, but with the spatial advantage of have the spatial distribution of this irrigation. So we collected all this information and we built the numerical model, which requires some coding, some Python and shell scripting. And we were able to run our first models. We were fairly happy with the results of our first models. I'm presenting some of the results here because they indicated to us that the model was actually doing physics. The correct behavior of what will be a hydrological system was happening there. So what you can see in this first figure is the water table depth in each cell of the domain. And we were very happy because the water table depth close to the rivers was 0 or very close to 0. The same happens when you see the flow rate of the rivers in the domain. We were very happy because the measure flow rate of the biggest river in the system was very close to the value that we were obtaining from our numerical model. And a similar behavior occurred for the hydraulic. It has the behavior that we were expecting for this type of models. And the big reason why we were happy with these results is that this is an uncalibrated model. So we can improve this a lot by implementing a calibration procedure. This is what we try to do. But the first question that we asked ourselves when we wanted to calibrate this model was, what are the parameters that are really important for this calibration? So we conducted a local sensitivity analysis to try to identify these parameters. And we conducted this local sensitivity analysis by identifying 4 quantities of interest that for us were quite relevant for the overall behavior of the hydraulics in the entire system. One of them was the water table depth in the valley of the system. The valley of the system is the gray shadow area in the figure. The flow rate in the Ponte Lago Oscuro station, which is the station or the flow rate station that collects most or the biggest area of the Po River watershed, and also the subsurface storage and the surface storage. Because again, our objective here is to use this model for water management. So for us, it's very important to understand what is happening with the water. Where is it going and how is it moving? Okay. So we conducted this local sensitivity analysis, one at a time sensitivity analysis, and I am presenting the results here. Here, each bar is representing one of the quantities of interest that I previously introduced, and the width of each one of these colors is representing the influence or the relative influence that each one of the model parameters has on the quantity of interest. I have 6 values of, for example, hydraulic conductivity only for the reason that I have 6 geomaterials. So the first hydraulic conductivity refers to one geomaterial, second geomaterial, third geomaterial, and so on and so forth. The conclusions that we can draw from these results are that hydraulic conductivity, especially the hydraulic conductivity of the first 4 geomaterials, dominate the behavior of the water table depth in the valley of the system and of the flow rate of the Po River. And the second big conclusion that we can draw from this figure is that the value of the Manning roughness coefficient 2, so this eta 2, which is the Manning roughness coefficient of the channels in the system, is dominating or is partially dominating the flow rate of the Po River. So with this information, we decided to continue with the calibration of 2 groups of variables. First, 4 hydraulic conductivity parameters, and second, 1 Manning roughness coefficient. We decided to divide this calibration in 2 phases. In the first phase, we are going to calibrate hydraulic conductivity parameters on the base of steady-state simulations using water table depth observations. And in the second phase, we are going to calibrate Manning coefficients using transient simulations and river flow rate observations. The only reason for separating this process in 2 phases is because running steady-state simulations has a lower computational cost, meaning that we can reduce the total computational burden of our calibration. And also, hydraulic conductivity is a parameter that can be calibrated with the outputs of a steady-state simulation. This is something that is not happening for the Manning coefficient. So for this first phase, we decided to conduct this calibration following a stepwise calibration strategy. So in a stepwise calibration strategy, you calibrate by steps. And in each step, you are going to calibrate one of your parameters by keeping all the other parameters constant. The second step, you are going to calibrate another parameter, keeping the remaining parameters constant, and so on and so forth. This is the strategy that we follow. But we faced a big problem here, and it was, again, the computational burden. The computational burden of running all the simulations that we wanted to actually calibrate as well as possible this numerical model, because we simply didn't have enough computational power. So we rely also on surrogate modeling techniques. We tested different techniques, polynomial expansion, Gaussian process regression, and neural networks, and we decided to go with Gaussian process regression, which was working the best to represent water table depth surrogates of the full numerical simulations. We calibrate our model against observations of water table depth in the entire domain, mainly in the valley of the domain. We collected the information of more than 1,000 wells, and we computed a temporal average values for each one of the wells and used those values to calibrate the model. The calibration itself was followed this procedure. So first, we run a limited number of simulations of the numerical model, so the par flow simulations, and estimated the water table depth in the entire domain for each one of these simulations. Then we compare those simulations with the observations and computed an error metric. And this is what you can see in this plot, the values of that error metric for different values of one of the conductivity parameters. Then, using the outputs of these simulations, we constructed the surrogates following the strategy that I mentioned before. And we were able to basically recover this line, a line that is telling me what is going to be the error or the value of an error metric for a given value of the hydraulic conductivity. Then, using any optimization algorithm, we use a very simple optimization algorithm here. We identify the optimal value for our loss function or for our parameter. That process was repeated several times. Actually, we completed 2 complete cycles. And we conducted a total of 8 steps to finally calibrate the conductivity parameters. In the first cycle that you can see in cyan color, the errors were decreasing rapidly. But then for the second cycle, we identified that errors were more or less stable, meaning that we could finish the calibration process at this point. Then, using the optimal values that we identify for these conductivities, we ran another numerical simulation of the Po River district. And we analyze the spatial distribution of these errors. The spatial distribution of these errors is telling us that our model is behaving particularly well in the valley of the system and is having problems to predict water table depths close to the mountains of the system. More or less 90% of the errors are smaller than 10 meters, and 50% of the errors are smaller than 2.5 meters. And you may be wondering, well, 2.5 meters is a lot, and I will agree, 2.5 meters is a lot. But considering the scale and the spatial resolution of the system, which was using cells of 2 kilometers by 2 kilometers, errors of 2.5 meters are actually acceptable. And when we compare the results of our simulations with results of previous research, the results were actually pretty similar, with the advantage of our model that it was considering not only subsurface processes, but also surface processes and the interaction between them. That was the calibration of the hydraulic conductivity parameters. Then we proceeded to calibrate Manning coefficients. For that, we use the outputs of our numerical simulations. When we run the model in transient conditions, we get this information. We get the runoff or the discharge or the flow rate in each one of the cells of our systems. And this is a function of time. Then we can simply use the values observed in different flow rate stations to compare the results of our simulations and eventually conduct the calibration. We collected the information for more or less 45 flow rate stations in the system, 45 flow rate stations in the system, and compare the results of our simulations with these observations. These are the results or the comparison of the flow rate of our model with the observations, the flow rate predicted by our model with the observations of the biggest flow rate station in the domain, which is again the Ponte Lagos core station. We were again very happy with these results because again this is an uncalibrated model, so this can be improved. And the strategy that we followed to calibrate this model was to basically run several simulations with different values of the Manning coefficients and compute an error metric for each station and for each value of the Manning coefficient. Then we constructed a cumulative distribution function of the KGE metric, the Klein-Gupta efficiency metric, and basically identify which was the optimal value of the Manning coefficient from this figure here. Basically, in this figure, the most or a line that is more to the right of the figure is better. Is representing that the model is capable to predict better or to represent better the observation that you have of your system. This is what we did. We selected a Manning coefficient of 7.5 times 10 to the minus 6 hours over meter to 1/3. These are very weird units of the Manning coefficient, but those are the units. And we finally compare the or visualize the error metric, the spatial distribution of the error metric. And that's what I am presenting here. Basically, with this information, we can conclude again that our model has a hard time trying to predict what is happening close to the mountains. The worst error metrics are close to the mountains, but our model is actually very good to predict what is happening in the valley of the system. Which again is is very good that we are able at least to have a very good representation of the value of the system, because there is where most of the anthropic activities occur. Irrigation and pumping is happening mainly in the valley. So we are actually very happy with the results of our calibrated model. And just some final messages of this very quick presentation. This was the first time that a numerical model of the entire Port River district was built and calibrated. This one of the first hydrological models of such a scale and richness of physical processes being calibrated. Usually, they simply cannot be calibrated. And it was possible to calibrate it because we integrate multiple methodologies in order to do so. But the good news is that these methodologies can be fully transferable to other domains. Eventually, it's going to be possible to calibrate other systems, other large-scale systems, using the methodology that I presented here today. Right now, we have a model that works and a model that is calibrated. So now we want to use this model. And for this, we want to conduct some scenario analysis. We want to know what is going to happen in the Port River district under different climate change conditions, under different water development scenarios, and in different land use scenarios. And that's what we are doing right now. So yeah, that was the story that I wanted to present today. Thank you very much, and I will be happy to answer any questions that you may have.
Okay, so thank you, Leonardo, for this really great presentation and a very detailed one. So I'm inviting everybody who is attending online to post their questions in the comments, and I will then read them out. While we wait for questions to come, I will start with a couple of questions of my own. And well, first of all, just out of curiosity, I wanted to ask you, what is the time that you require to run a full numerical simulation with the model, just to have an idea of like how much time then you save when you use surrogate models?
Yeah, so to run a numerical simulation, we estimated a computational burden between 200 and 1400 core hours. This means that if you are running this in a 40-core computer, it may take between 5 hours and maybe a complete day, 24 hours. This varies because some parameter values are easy to solve by the numerical solver than others. But this is the time that you require to run a complete numerical simulation. Now, with the surrogate model, once it is ready, it takes a fraction of a second to predict the outcomes of your numerical simulations. So the savings are just a lot. It's just a crazy number.
Yeah, it's a lot, of course. And then, I mean, it's not my field of research, but I was wondering that when you collect different types of data, you always have like different temporal and or spatial resolutions of your data. And I mean, how do you manage with that when you have to use those data to calibrate your model or to compare your results with the data themselves? Or
So yeah, this is a challenge. This is super hard because you have multiple sources of information that collect the information that you need in different ways, different qualities, different temporal resolutions, and it's simply not possible to get all the information that you want in the way you want. So you have to, as I was mentioning in the presentation, you have to make some assumptions. And you have to make some acceptable assumptions with the information that you have at your disposal in order to reduce as much as possible the uncertainty of your outcomes, but make it feasible to conduct your simulations. We simply had too many different sources of information for the different variables that we need. So it comes to my mind right now, the reconstruction of the hydrogeological reconstruction that was conducted by my colleague. Information was taken from 3 different national authorities. And again, all of them have the information in different formats. different spatial resolutions, and it was very hard to make all that uniform. And actually, one of the results that he was obtaining, or he obtained, was that his predictions were very uncertain in the mountain of the system, which is just like that. I mean, we have to accept that uncertainty in the mountains of the system in order to be able to run the entire numerical simulation. And maybe some of that uncertainty was the main reason why our numerical outcomes in that area of the system, in the mountains, were not the best.
Okay. Thank you very much, Leo. So I don't know, do we have any other questions from the studio or from anybody online? I don't see any questions online coming for now. I don't know, Sang, do you have any questions?
I have one very short question, also coming from someone who's not expert in modeling. I was surprised to see that your initial results, uncalibrated one, came out quite well with the good fit with the data. Could you describe how that happened? Is it purely by luck, or you started out with a good quality of the data, or do you know if the system itself is quite simple or predictable?
Is a bit of luck, I have to say, a bit of luck, but also all the information that we use to construct this first model was built upon the base of previous research. So the first value of hydraulic conductivity that we use was actually taken from previous research in the area of the hydraulic conductivity parameters in general, of the different geomaterials. And the same happened with, for example, the Wangen-Uchten parameters. We didn't have a value for the area, but we have values reported in other systems in other parts of the world. So we use those values, which were reasonable, but we weren't sure how close these were to the actual values in our system. And we saw that actually they were good. They were not bad. We were able to represent the behavior of the system quite accurately. But of course, they could be improved, and that's what we get from the calibration. The errors were decreased by a lot when we calibrated the model.
Thank you.
Great. So I think we have no more questions, and we can move to the second speaker.
Thank you.
Thank you, Leo, once again.
Now I'm excited to introduce our second speaker of August session, Tracy Amaka Chukwuma. Tracy is currently a PhD candidate in hydrology at the University of Georgia, focusing on geologic carbon storage and environmental remediation. She holds a bachelor's with honors degree in geology from Nnamdi Azikiwe University in Nigeria. She possesses a combination of academic research and industry experience in reservoir characterization, digital rock physics, and petrophysical analysis. Her research centers on improving the characterization of CO2 storage systems by combining X-ray, micro-CT, and SEM imaging with hybrid scale models to simulate reactive flow and transport processes in the subsurface. So we are excited to host Tracy. And Tracy, the floor is yours. So whenever you're ready.
Thank you, Sang, for that introduction. And I also want to thank the entire Porous Media Tea Time Talk team for having me here for this opportunity to speak about like a part of my work. So yes, my name is Tracy, and I will be speaking on the evaluation of structural changes in some complex heterogeneous rocks using multiple techniques, and these techniques span a plethora of like scales. So as an introduction, I would say dissolution reactions, most of us are conversant with them. They are pretty much very common in natural environments and also pretty important in engineered processes. One of such engineered processes would be geologic carbon storage in saline aquifers, where usually when CO2 is injected into brine-saturated formations, this CO2, first of all, undergoes like aqueous dissolution reactions with the in-situ brine. And then you have acidification of this brine when H2CO3 is created. And then that also propagates mineral reactions with the host rock and the acidified brine. So of course, dissolution reactions are very important in those kind of subsurface systems. For another engineered process that dissolution reactions are really important is in reservoir stimulation, usually for resource extraction. It's very important in fields like geothermal extraction, oil and gas exploitation. And usually in these situations, we're looking to enhance the transport properties of reservoirs by implying dissolution reactions in these reservoirs. So we're looking to improve permeability, improve porosity, so extraction can also be improved. And finally, in a more natural setting, looking at, let's say, shallow carbonate aquifers that are kind of exposed to atmospheric CO2 that usually dissolves in meteoric water and leads to some structural changes in these aquifers. In that sense, transport properties like fluid flow, permeability are affected as well. So looking at dissolution reactions in these settings are also really important. So dissolution reactions, because of how commonplace they are in these environments and in these processes, have been well studied for a while. But usually these dissolutions, these studies of dissolution reactions are kind of focused on single mineral formations like limestones, where we assume that most of the matrix is going to react in this process. But in our particular study, we were looking at multi-mineralic rocks like sandstones, where there's like spatial heterogeneity in the minerals that are actually involved in these dissolution reactions. So how then do we kind of model these dissolution reactions? First of all, we need to keep in mind what these dissolution reactions entail and how they affect reservoirs or formations that they occur in. Take, for example, again, in geologic carbon storage, where most people kind of tie dissolution reactions to mineral trapping, because as we said earlier, when the CO2 dissolved in brine reacts with the host rock, then you have this kind of release of reactive cations that can react with the CO2 to form carbonate minerals. So that's the precipitation aspect. So we need to keep in mind that when this dissolution and precipitation occurs, it leads to a change in the structure of these reservoirs. Now, when you have a change in the structure, that can affect things like the structure and stratigraphic trapping mechanism. And once you have that change in structure, you also have a change in your transport properties, things like your permeability. And that change in permeability can affect the migration of your plume. So you need to know that even though dissolution reactions are happening, there's also an effect on some properties as well. So we need to look at these dissolution reactions both in their causality as well as in their effects. If you look at this schematic from the work by Yuan Li, you can see here that usually based on grain size distribution as well as spatial distribution of these grains, sometimes you can see a difference in concentration gradients for reacting fluids based on the arrangement of your porous structure. Now, why I'm highlighting that is because typically standard form of modeling dissolution reactions are usually continuum approaches. For continuum approaches, it's kind of where you average the microscopic properties of the pore scale. So you average those properties into a larger scale model or volume, so you don't take into account the uniqueness of the rock structure in your modeling. And that's an issue because most of the time you can see here that just by changing the arrangement of grains, sometimes, which we know that for heterogeneous rock samples, they definitely do not have simple geometries like typical continuum scale approaches are set up as. So we can see that just by averaging out that complexity of pore structure, we likely will not get very accurate results for predicting dissolution reactions. So aside that, you could also see at the bottom here with the reaction rate equation for dissolution of calcite that there are some parameters like the surface area of the reacting mineral that is very important for your dissolution reaction modeling. So things like that are usually more accessible at the pore scale, but continuum scale models or approaches address things at a larger scale called the continuum scale or the Darcy scale. So to accurately characterize these mineral reactions, we need to take into account the spatial heterogeneity of our structure, our rock structure, the mineral abundances we have, and how the distribution of these reactive minerals are in our rock structure, the elemental content, as well as how accessible that mineral is to pathways in which the reactive fluid is going to access these surfaces. So that kind of leads us to our motivation. Like we said earlier, we're trying to look at simulations at kind of the pore scale. Here, the pore scale is defined as the scale where at each point in space, it's kind of occupied by one or another phase. It's either a pore or it's a grain. But even though we're looking at the dissolution fronts occurring at the pore scale, we're interested in the effects or the change in macroscopic properties at the Darcy scale. The Darcy scale is simply the scale where we view both pores and grains simultaneously as a continuum. So that simply means we need to integrate both these scales in our analysis to get more accurate characterization of dissolution reactions. So since we've kind of identified that we're going to need to kind of represent multiple scales or dual scales, that means for our analysis technique, or we need to employ like a multi-scale, something that spans across multiple length scales to do our analysis for predictive dissolution reaction modeling. So for that, I just kind of put this to remind us that we're working across multiple length scales. For us, we start with core flooding experiments at the centimeter to millimeter scale, then X-ray micro-CT imaging at the millimeter to about micrometer scale. And then you can also do analysis with SEM on thin sections at the micron to nanometer scale as well. So it's a multi-scale workflow. You're using multiple techniques, so it's multimodal, and we're trying to model the impact of dissolution reactions in these multi-mineralic rocks like sandstones, which are a bit more complex. So for that, I come into the kind of approach that we use for this. This is where the field digital rock physics comes into play, which is when we try to build digital representations of the porous media we're working with, so we can carry out flow and transport simulations on these digital models. Now, how this works, it's kind of based on advanced or high resolution imaging. That's why we rely on X-ray micro-CT and as well as SEM imaging. So the thing is, once you get this digital representation of your porous media or your rock sample, you can then extract the pore geometries from that and do your simulation in those geometries. Why that's very important is most of the time for complex experiments that, let's say you've done the first time and you've validated your model on that experiment, and you probably need to go back and change a parameter like concentration or flow rate. Setting up that entire setup to run another experiment just to vary a parameter can be both time intensive and resource intensive. So most of the time, you can just use your digital rock physics model to do a simulation of a slight change in parameter, which kind of cuts down the expense and the effort as well. But digital rock physics also has its limitations because it's based on imaging, which also has its own limitations. Aside that, it's not a standalone solution. It usually relies on validation from experimental data as well. But I'll be speaking on some of the limitations we faced while trying to employ this process. So just as a quick example, I'm sure we're all kind of conversant with X-ray micro-CT imaging, but just a quick refresher, this is kind of an imaging technique that relies on density attenuations of X-rays passed through a porous media or a rock sample in this case. This is my particular sample, which it's one of the samples we worked on, but this is the primary one I'll be speaking on throughout this talk, which happens to be the Carbonate sandstone, and it was imaged at about 4.7 micron voxel size. That's the resolution of the imaging. Now, I just want to use this to show the different phases, how they are represented in X-ray micro-CT imaging. Now, the composition of this particular sample it's mostly made of quartz, some carbonate minerals, and some clays. So from this, we can see that most of the matrix, which is the quartzic matrix, are reflected as this light gray, and most of the carbonates are seen as this white in here. Because we said it's based on density attenuation, that means that phases that are very low in density, like the pores, are reflected as very dark material in our X-ray micro-CT images. So you can see this from our segmentation, which is simply a way that we separate the phases based on gray levels in the X-ray micro-CT imaging. We were able to identify our carbonates, our macropores, which in this case we're identifying as all the pores that are fully resolved at this 4.7 micron resolution. So they are all the pores that are above the resolution of imaging. And then we also identified a kind of intermediate phase, which we labeled our microporous zone. We assume that this zone has a lot of pores and solids intertwined that are kind of below the resolution, the imaging resolution of 4.7 microns. So we will further analyze this sub-resolution features as we go on in the slides. Now, you might be asking, why are there like micropores if we're already imaging and we want to use this particular technique for our analysis? The thing is, there's always, in X-ray micro-CT imaging, there's always a trade-off between resolution and field of view. Now, that trade-off most of the time simply means if you want higher resolution images, you have to reduce your sample size. But as we know, rocks are so heterogeneous in nature, we want as much of a representative volume as possible to get more replicative results to what is happening in the real porous media. So most of the time, you have to find that sweet spot between your field of view and your resolution. But we will address how to overcome these sub-resolution features further on. So while we were looking at the structural evolution that occurred due to dissolution reactions in this particular sample, I just want to preface by saying the core flooding experiments were carried out in Auburn University, who are our collaborators, and the very first X-ray micro-CT images, the ones at 4.7 micron resolution, were done at Auburn University. So we just tried to replicate a mock geologic carbon storage system. This is why we have NaCl here as brine and CO2 as the injected CO2, just to replicate that system. So X-ray micro-CT imaging was done on the core before the core flooding experiment and after the core flooding experiment. Now, after we get the data set from those two, we worked on the analysis over here, which includes reconstruction of the 2D horizontal slices into a 3D volume, filtering. Afterwards, we also did registration. registration is simply trying to make sure that you are at the same location in both the data sets. Then when you have perfectly registered data sets, you can subtract one from the other. So that was the first technique we used, which is called differencing, where we subtracted the unreacted data set from the reacted data set to get just what changed after the core flooding experiment. Now, how we analyze that is we also do segmentation, which I've explained how what that entails, but we use two methods for our segmentations. We used the watershed technique, and then we trained a machine learning model on some part of our data set, and then applied that to the rest. Then we compared the results from both, and we had pretty replicative results between the two. So we also kind of segmented both data sets apart from the differencing, just to do our analysis and get the structure, like the porosity, get the porosity change between the two after reaction. So as we said earlier, we had already identified that there was a microporous zone, which is the zone or the structures that fall below the imaging resolution. So to kind of analyze that, we supplemented the X-ray micro-CT imaging with SEM, scanning electron microscopy. First off, to look at the structures of these sub-resolution features, we use BSC, which is backscattered electron feature, to look into that. And we were able to identify that there was a lot of porosity in brecciated grains, very porous or dense, like agglomeration of clay as well. So we're able to identify that this is the micropores within the microporous phase. This is how they occur mostly. And then we used the energy dispersive spectroscopy feature for SEM, which gives you the elemental analysis of what you're looking at. So we're able to deduce that most of the microporous zone was made up of quartz and a bit of clay. So what that simply means is for the dissolution reaction, we don't expect the microporous phase to have a lot to do with the dissolution reactions, but they do contribute to transport and flow in the particular sample. So then trying to quantify and look into exactly what changed, our data sets are from 3 volumes at the inlet, midpoint, and outlet of our core sample. And one thing we noticed was the same dissolution pattern throughout the sample, which kind of gives us the inference that the sample is quite homogeneous all through, and the same kind of dissolution pattern, which was uniform dissolution, occurred throughout the sample. So we were able to identify that most of what dissolved were the carbonates. We were lucky because these carbonates were above the imaging resolution, so we were able to see that dissolution process through our 3D renderings of our volumes, sub-volumes. But then we decided to do a slice-by-slice porosity analysis on the X-ray micro-CT image, and these are the porosity profiles you get from that. The dark black is the unreacted profile, the gray is the reacted profile, and we're able to kind of calculate and estimate about 6.7% increase in porosity from that dissolution reaction that occurred. To kind of validate what we got and our inferencing that it was mostly the carbonates that dissolved, we validated this against effluent chemistry from the core flooding experiment, as well as weighted differencing. Then we also calculated slice-by-slice porosity analysis for pores created, which we calculated from the differencing method I introduced earlier. So the differencing method was used to create one pores created profile, while the second way we calculated the pores created was subtracting this slice-by-slice porosity profile for the unreacted and the reacted from each other. And as you can see here, the 2 pores created curves, they are closely related, they are correlated. We now compared those 2 pores created profiles through the volume to the carbonate profiles through the volume. And if you look here, you can see that for the pores created, it's also very closely related to the carbonate profile, which kind of validates our initial point that it's mostly the carbonates that are dissolving in this particular sample. But then, based on the measurements we got experimentally in the lab with our helium pycnometer, we know that our unreacted sample's porosity is actually about 20%. But if you look at the porosity analysis slice by slice we worked on, you can see that that falls within the range below 10. It was actually 6.8%. So for this particular micro-CT imaging that we did at 4.7 micron resolution, that simply means we were not catching most of the porosity. Most of the porosity is actually below the resolution of the imaging at the time. So we were able to address that in multiple ways. First off, for the low resolution micro-CT, we call it low resolution now because we acquired higher resolution micro-CT at an imaging resolution of about 0.6 microns. And we did that here at UGA because we got a new equipment, so we were able to. So for the low resolution X-ray micro-CT, we then decided to evaluate the parameter, the microporosity parameter. And this is kind of the formulation we used for that by introducing a mean intrinsic microporosity factor. That factor is multiplied against your macroporous zones, the fraction of your macroporous zones to give you your microporosity. This microporosity is based on this kind of relationship in bold black here, which is where you relate the average gray level of your microporous zones to the average gray level of your voids, being your pores, and the average gray levels of your matrix or solid. When you calculate that microporosity, intrinsic mean microporosity factor, you then multiply it against the microporous zones fraction in your entire volume. Then you get the microporosity of that volume. We then added that to our macropores to get our total porosity from the low resolution X-ray micro-CT. But for the high resolution X-ray micro-CT, if you remember earlier, I did say there's a trade-off between field of view and resolution. Because we increase the resolution, this volume is way smaller than the initial low resolution volume we initially imaged. This volume is actually a 0.7 millimeter cube. Yeah, cube. We made a smaller cube out of the actual sub-volume we were working on to get this. And even at this resolution, we didn't get all the microporosity zones pores resolved at this resolution, but we did calculate porosity from this. Then we also stitched together high resolution BSC images to also calculate porosity. But keep in mind that for SCM analysis on thin sections, this is in 2D. So the other two, the two X-ray micro-CTs are 3D, but this is 2D. But we just did that to evaluate what we were getting from the low resolution evaluation process as well. So this is kind of the result of what we got from that. In the black and the very first curve, you can see that this is the porosity value we had before we did any of the multi-scale evaluation. This is 6.8%. And by the time we applied the microporosity factor to calculate our microporosity and added that to our macroporosity, we then increased our porosity prediction to about 17.3%, which can be seen in red. Then also the other validations we carried out, like the stitched SCM images, the porosity calculated on that was about 17.9%. And for the sub-volume that we worked on, the smaller field of view we worked on to get higher resolution X-ray micro-CT, we got about 15.3%. Now, what this kind of means for us is that if you can also look at the profile, it has a little bit more variability in it than for the larger subvolumes. That simply means this is below our representative elemental volume, which is a REV. A REV is simply the volume of size that gives you or yields consistent results for the property you're looking at. So to us, we were able to identify that this is kind of low. We got 15.3% from that because it is below our REV. It is not representative enough of our sample, but pretty much we were able to improve our results from our analysis by carrying out those multi-scale evaluations. So aside porosity, for our permeability, currently we're applying a microcontinuum approach to represent that multi-scale aspect, that dual scale aspect, because with the microcontinuum approach, you kind of integrate in one computational domain both the pore scale and the Darcy scale, or the small continuum scale. And then in that, you can solve one set of governing equations through the entire computational domain. Now, the kind of fluid flow equation that this is based on is the Darcy-Brinkman-Stokes equation. And this equation is very important because it's implicit and it can tend asymptotically towards whatever scale you're interested in. So it depends on how you grid the structure you're working on. If you grid the structure and identify a cell as purely porous, then the equation is going to the equation that is going to be solved in that particular cell is going to be the Stokes equation, which is for fully resolved domains. And then if you identify another phase as maybe the microporous phase that we had, which is a mix of both solid and fluid aggregates, or porous space. It's a mix of both. For those microporous phases, Darcy's equation will be solved in those spaces. Now, what's kind of the breakdown of this particular Darcy-Brinkman-Stokes equation? On the left-hand side is more like the inertial terms, where we have a bit of our porosity, and we also have like we also have a flow field on the left. And towards our right, we have our pressure gradient, we have our density, we have our gravitational constant, and then there's a viscous term here attached to our velocity gradient. But what is more interesting to me is this function just after the velocity gradient, which happens to be our drag force. Now, the microcontinuum approach is built in a subgrading way, which means, as I said earlier, the way you set up your grids is how your governing equation will be solved through that particular flow cell. For this, the drag force is only present in cells that are an aggregate of both pore space and solid, so pretty much the microporous phase. When it is in the fully resolved phase, which is the pore phase, it tends towards zero. What does that mean? It means that particular factor disappears from the equation when we're solving in the resolved pores, in this case, what I called macropores. But if you're in this space that kind of is a mixture between the two, which is our microporous phase, that drag force is predominant in it, but the inertial force tends towards zero. So this is what we mean by the Darcy-Brinkman-Stokes equation can tend asymptotically towards what kind of phase you're dealing with in your cell. So just as a quick recap of what we kind of presented, first off, it's mostly the carbonate minerals that we identify as what were involved in the dissolution reactions. Then our increase in porosity was also validated against our core flooding experiment, effluent chemistry, weighted differencing, and as well as comparison of the pores created curves, slice by slice analysis curve with those of our carbonates throughout the volumes. Then aside that, we're able to identify that most of the porosity was actually below the resolution of imaging, the initial X-ray microcity imaging at 4.7 microns was not enough to capture most of the porosity in the volume. So we're able to supplement for that with other analysis. And presently, we're applying a microcontinuum approach to kind of evaluate and determine our permeability in our structure. We will also validate that because we have experimental measurements of permeability from our core flooding experiment. And in the near future, we are also hoping to run reactive transport modeling simulations on our core volumes, and that will be validated as well with effluent chemistry from the core flooding experiments. So I just want to thank the people who contributed to this particular project, which is first off my PI and supervisor, Prof. Charlotte Garing here at the University of Georgia, and our collaborators in Auburn University, Professor Lauren Beckenham and Zulfan Shi. And with that, I would say thank you, and if there are any questions.
All right. Thank you, Tracy, for the wonderful presentation. And now the floor is open for anyone in the audience to ask questions. While they're formulating their questions, I have one question, Tracy. Can we go back to the conclusion slide?
Okay.
Yeah, in the second bullet point, you mentioned that you were able to compute the porosity, and then it matched with the results you obtained from the effluent chemistry analysis. And I was thinking if it seemed this could be maybe a case because your core sample was structurally fairly uniform, it seemed.
Yes.
If it were different, let's say if the porosity heterogeneity was quite high,
yes,
do you think this will give a hard time in predicting or computing porosity of the entire core or system?
So we're
using your methodology, yeah.
Yeah, so we're actually also replicating this process with a more clay-rich sample. That sample has a lot more clay. The porosity is a bit more varied throughout. But so far, we are seeing that kind of applying the same processes, especially the incorporation of the STEM, the BSC, and the EDS is really kind of helping us get the same kind of porosity deductions that we did from this more homogeneous sample. The only differences that we are kind of identifying is that for that sample, a very different dissolution regime was introduced or pattern based on the Peclet numbers and the flow rates for that one. So that was the major differences we were seeing in the analysis. But pretty much the deduction of the porosity was pretty much spot on with what we got from this as well. It's just the dissolution regime that's different. This is uniform. That was more compact with like wormhole in it. But yeah.
Yeah, it will be interesting to see the results as well.
Definitely.
Thank you.
Thank you.
Yeah. We have one question from the audience from Aderoju Raymond. So the question is, Tracy, you stated the X-ray microcity imaging has a resolution and field of view trade-off. Why is it still preferred?
Okay, so this is a very interesting question because we always address this when we try to introduce X-ray microcity to any workflow. So X-ray microcity, despite its limitation, is still quite very helpful. First of all, it's non-destructive. It's not like if you need thin sections for SEM that you have to kind of slice through the core sample and over time kind of change the structure of the rocks in minuscule ways. For this, the rock structure stays intact, and then you can image it. It's non-destructive. You can reuse that core sample for other experiments as well to be able to perfectly match the results you get from X-ray microcity to, let's say, core flooding experiment. And for X-ray microcity, you actually get a 3D representation of your volume. yes, with SEM, you do get higher resolution imaging most of the time, but we need to remember it's 2D. So X-ray micro-CT is still a very powerful tool because you do get 3D on kind of adulterated representation of your porous media to do most of your modeling work on. So, yeah.
I have a follow-up question. I don't not have much experience with X-ray CT, but how long does it? I know it may depend on the resolution, but and the field of view, but how long does it typically take for your case to obtain the 3D image of an area that you're looking at? And is stitching those images to image the entire, maybe the core, is it really challenging?
For the stitching with the SEM, it is quite challenging because you have to be zoomed in and you have to like have this walkthrough pattern through the entire thin section. And you need to remember that is just one slice of the entire core for the stitching. So at the end of the day, it's so labor intensive and it's just a 2D representation. For the X-ray micro-CT, you kind of already answered the question. It is really based on the size of your sample and the resolution you're going for. But the larger samples at lower resolutions that were taken at Auburn University, I'm not really sure about the time frame. But for the higher resolution, smaller samples here, it can take, let's say, anything from about 24 hours to maybe slightly something into your second day. So it depends, though, the resolution you want, the size you're working with, but to get something really good, sometimes it takes a while. Yeah.
Thank you. I think it may also depend on how long you want to spend your years for your PhD.
I would say.
Yeah.
Yes. Thank you.
I don't think we have any other questions, so I think we can conclude your talk now. Thank you, Tracy.
Thank you.
Okay, so that was the end of our August session. And for the September, we have Spanish National Chapter Special. We're hosting two young early career researchers from Spain, Caterina and Alejandro, which will be held in September 23rd. So please join us in September. And this session and so forth is brought to you by the Young Academy community of the Interpol, which are composed of early career researchers and scientists around the globe, like you guys who are watching this. And if you like to present your research, or you have a colleague, friend who are doing an interesting research on porosity media, please contact us at this email shown on this slide, and we can schedule your talk. And thank you everyone for your attention and time. And I hope to see you again in our next session. See ya.